it covers that, but nothing else. So for example, testing that we are going to do today is not included. The confidence interval is not included. So how to prepare this? It says redo homework 1 to 5, okay? So do it, please. You have all the solutions and everything. It also says homework 4 and 5 are the most important. What does it mean? If you do this, then you'll be pleased, okay? You'll be happy that you redo these exercises. So please do this. Redo quiz 1 and 2. So especially the second one, because I saw that at least half of students have some trouble here and there. So make sure that you know everything in that quiz. Okay? I check it. I check it in the exam. Also, it says there will be an R question, just like the second quiz. Maybe a little bit more extended than the second quiz. It also says solve sample midterm. Did you do it? Have you tried? And it says solve the past midterm. So I'm going to pass this past midterm today. So these 4 are the musts. So you have to do all these 4. Okay? If you still have time, then you may solve exercises in the textbook. That's extra to make sure that you get 100 out of 100. But if you do these 1, 2, 3, 4 things for sure, repeatedly, and make sure that you get at least 70 or 80. Maybe something like 75. So my plan is to give you 5 questions. Out of 5, about 3 or 4 will be from these sources. Okay? Do you understand what I mean? I'm not going to repeat the same question. I may just change a few things here and there, the way I ask the same question. But basically, it will be the questions from these sources. So make sure that you study these materials very well. Okay, so do you have any questions? So the question is, are you going to use the computer when you solve this R question? The answer is, of course, yes. You're going to use your computer, okay?
How long does tests?
It's 70 minutes. 70 minutes, 5 questions. So it depends. So did you try it? Did you try the sample midterm? So let's consider exercise 3. So basically you have data points, 8 observations. Okay, so how do you run a regression? The idea is you calculate the sample variance and sample covariance from the observations. Can you imagine that you can do such a thing? You can use R to do it, okay? You type the data, X gets blah, 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 Y gets blah, 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 and you find out the variance and covariance. And beta 1 hat is a ratio of covariance and variance. And you know how to get beta null hats. Is it how you solved it? Okay. So exercise 3 is kind of things that you have to know, but it's one of the easier questions if I ask this question again. What about exercise 4? It says, what is the effect of this change in class size on the average test score? So if you change your x by some unit, like delta of x, what is the changes in y? Do you remember? Right? So if you remember this, you can solve it very easily. So this is for exercise 4. Now B, find the R squared. So mostly the easiest one is to find out the sample correlation coefficients and you square it, okay? So this is the sample correlation coefficient, right? You already have all these components, and if you square it, that's the R squared. Something we did a lot, right? So I think you can solve this exercise 4. What about exercise 5? So how do you find out the sample variance of X? So previously, what is given was something like this, right? Summation of xi minus x bar squared. So for example, we have a number for this quantity, right? But right now, we only have this. And of course, they are very different, right? So how do you find out the sample variance? Do you remember these shortcuts you learned in statistics? Oh, you have to divide by n minus 1, right? So they are the same thing. So in statistics, we learned that summation of xi minus x bar squared is equal to summation of xi squared minus and the sample size times x bar squared, the sample mean squared, right? So you can use this formula to get the sample variance. What about the sample covariance? Sample variance of y now you can use those 5 quantities and you can find out the sample variance and sample covariance very easily. Now let's consider exercise 6. A is easier, right? So sample covariance divided by sample variance, something like that. B, we always use this formula, okay? R squared, capital R squared is a small r of R squared. Sample correlation coefficient squared. And you can write down the interpretation. So I want to see these harder. So how do you get the SCR? So that's the definition, right? So if you know SSR, you're done, right? Because the sample size is given, 15. So how do you find out the SSR? So SSR is here. And in part B, you're going to find out the R squared. So what is missing here? TSS. If you know TSS, then everything is just works very smoothly. So how do you find out the TSS? That's the key.
Variance of y.
So for this, you now remember the definition, right? So that's the definition of the TSS, total variation. But the sample variance of y, use the same definition. The only difference is n minus 1 factor, normalization. So TSS is n minus 1. Now this is given in the question. N is 15. Find out TSS. You plug it here, you find out SSR. Plug it here, you find out SCR. Now this is a very typical question from chapter 4. Okay, so you have to make sure that you know how to solve things like this. Now, how do you find out the ESS? There are at least 2 different methods. But the easier one is just use TSS is equal to now this is known from D. So you can find ESS, right? Is it clear? Now let's consider exercise 7. Read it, please. So how do you find out A, part A? CS class size gets 21, right? Just plug 21 in the equation. Okay, how about B? So that's how you do it. Use this. What about C? So the average class size is 21.4. That's 21.4. This is 530. This is minus 3. That's how you find out the average test score. Okay. What about D? Can you do D? Can you try right now if you haven't? Can you try D? Now, what is the sample standard deviation of test score? So let's use it. Sample variance is TSS divided by n minus 1. Right? Because by definition, this quantity is the TSS. So n is given. If you find out TSS, you're done. Right? So how to find out TSS? R squared is given. So that's one clue. What else is given? SCR is given. So you walk backward, okay? So from here, you find out SSR. And here, you find out TSS. You plug TSS, then you can find it, okay? It's basically, it's the same question. I just ask the same question in a slightly different way. As you see, the key is to memorize a few of these quantities. If you don't know the definition, then there's no way you can address these questions. Okay? If you haven't, make sure that you try this on your own without looking at solution. That's very important. Reading solutions does not mean that you understand them. So two very different things. You can read it without actually knowing anything about that solution. So how do you find out that you actually know the question? The only way is to try it without having any solutions, okay? So I was kind of hesitant to pass out the solution for these sample problems, but because of the time constraint, I'll give you a solution. But again, if you haven't, you have to try them without any solution. That's very important. Actually, that's a key step. Okay, just to make sure that you understand this, what we do today, which is the hypothesis testing, is from chapter 3.2. Now, is it a part of the exam or not? It is not, okay? So don't be confused. So this is included. It is included. This is included. It is not. But you have to know the sample variance anyway. Sample covariance. And this is certainly not included, okay? It's a review of statistics, so I just like to give you one example, and then I hope that you can fill the gap, okay? We cannot just discuss the whole thing because it takes more than a month to discuss everything about the testing. So in a typical situation, we have two competing hypotheses, and then you can make two actions, two decisions. And one hypothesis is called the null hypothesis, H null. And the competing hypothesis is the H1, alternative hypothesis. Typical example is this. There's a crime scene, something like that. Maybe you can imagine some kind of blood on the floor. And there's a suspect. Okay? There's this guy who looks very suspicious. The two competing hypotheses, the null says he's innocent. Just as an example, alternative says no, he's guilty. He's the guy. So we have two hypotheses. What kind of decision we have to make? One kind of decision says, so just by convention we says, we reject the null, and we do not reject the null. So that's the two decisions we make. So the null says the guy is innocent. What does it mean to reject it? So this is the one hypothesis, and we reject it. So we reject that he is innocent. It means that we find him guilty, right? So it says that he's guilty. Find guilty. So you convict. You declare that this guy is guilty and maybe send him to jail, things like that. Do not reject the null. Being innocent means that you do not reject this idea that this guy may be innocent, so we do not find him guilty. Not find him guilty. And you acquit. Let him go. Let him free. So that's two decisions. So we have four cases depending on what is true, is he guilty or not, and our decisions. Now suppose that we are in this situation, although we never know whether actually he is guilty or innocent. Just imagine that we are in this situation. Is it a good thing to have things like that? So this suspect is actually innocent, and we do not find him guilty, which is a good decision, right? So it's good. What about this? So this suspect is guilty, and we find him guilty. We convict him. Send him to jail. This is justice. So it's good. So there are some chances that we may make good decisions, but not always. What about this? Now he is innocent, but we find him guilty. We say that this guy is guilty, although he's actually innocent. This is a wrong decision, right? This is a kind of error, and you may remember that this is called a type 1 error. Under this, he is guilty, but we do not find him guilty. This is a wrong decision. Call it type 2 error. So the idea of the testing is how to make a decision. You want to say that he's guilty or not, okay? The testing is about how to make this decision in a nice way, in an optimal way. And when we do that, we have to be careful, because sometimes we make good decisions, sometimes we make bad decisions. So the idea is we try to make the probability of these cases as high as we can, and try to reduce the probability of these two types of errors as low as we can. But there's a trade-off. If you decrease the probability of type 1 error, you necessarily increase the probability of type 2 error. And the other way too. It's impossible to make the probability of 2 errors both down. It's a way of life. It just doesn't happen. Just imagine these extreme cases. How to make sure that you don't make any of this type of error, type 1 error? How do you make sure that the probability of making type 1 error is close to 0? How do you do that? It's actually quite easy. You never reject the null hypothesis. All the suspects come in, you let them go. Right? So sometimes it is a good decision, but at least you don't make this type 1 error. But there is enough chance that you may make a lot of these types of error. So under such kind of circumstances, some kind of, how can I say, in the legal model that everybody just go. You are free to go. Okay? Whoever come in. Then you can reduce this type 1 error, but you necessarily increase type 2 error. Because sometimes you set the guilty person out. How to make sure that you never commit this type 2 error? Once you're a suspect, you just go to jail for sure. There's no even trial, right? And the probability of type 2 error is 0, but this probability increases, right? So this is kind of rough idea, but you can actually prove it. You can prove that there's no way that you can decrease the probability of these two things at the same time. So the model is in the legal system and in statistics, we somehow believe that this is more important. So we consider the probability of type 1 error first. Okay? Make sure that this probability is not bigger than something we can tolerate. Because it's impossible to make a perfect decision all the time. If somebody says, if the society says, if the probability of type 1 error, which means we have an innocent person and he goes to jail. That's that type of thing, event. If that probability is less than 5%, then at least it's tolerable. We can live with such a system. If that's the case, then that's the maximum probability of type 1 error we tolerate. So given that, we start to worry about this type 2 error. Okay? That's usually the case. Why? I don't know. Just a convention. So in the legal system, people say that the risk of putting an innocent person into jail is much greater than set the guilty person out from the moral standard. At least it's convention. Even in statistics, we believe that rejecting the null hypothesis wrongly is a lot riskier than the other case. So we care about this one first. So necessarily, the testing method depends on this guy, the probability of type 1 error. Okay? So this is very important. So in my presentation file, there's some story about this. So you can read it, okay? Let me introduce a few things. Again, there are 4 combinations. So what is this? We use a conditional probability, this notion. This is a conditional probability that the null is true, innocent person, the suspect is innocent, but we reject it. So this is the probability of type 1 error, right? So in statistics, we call it a significance level. And we use alpha for this probability. So the significance level is just the probability of type 1 error. And this is very important because we like to make sure that this alpha is not over some threshold, like 5%, 1%, whatever. What is this? The probability of do not reject the null if the alternative is true. So he's guilty actually. The suspect is guilty, and we do not reject the null hypothesis. So he believes that he's not guilty. Again, this is a wrong decision. There's a probability type 2 error, and we use beta for this probability. Now, the other side, he is guilty, and we reject the null, which says he is guilty. Okay? This is a correct decision. This is the opposite of beta, 1 minus beta, and this is called the power of a test. So the fourth one is 1 minus alpha. As you can see, there are only 2 degrees of freedom, 2 things you can move, right? So if you fix this and this probability, the third and fourth probabilities are fixed, given by the first 2, right? The convention is we usually choose the combination of first and third. It's the same as first and second because they kind of deterministic. So we care about the significance level. We try to minimize it, at least less than some level. And then we try to maximize the power of the test. So how to actually conduct a test? So that's a kind of a lively example. Now we are in a world of very dull statistics, very boring. So let me just give you an example, a simple example, and then hopefully you can figure out the other cases, okay? And then we start to solve the exercises. So how do you do that? It says, so this is the easiest one. Under the null hypothesis, for example, suppose that, we like to talk about the population mean of something. Suppose that the population is young workers in Korea. Ages between 24 and 32, okay? And the mu is their mean wages. So that's the population mean. We do not know the population mean because we don't have population. What we can have is a random sample out of it, right? The testing idea is just propose an idea, propose a question. Is the mean income equal to something? So that's the null hypothesis. The alternative usually says no, it is not, okay? So let me use that example. So let's consider something even simpler. Do you remember how to call this kind of null hypothesis? And you have an equality to a specific number. This is a simple hypothesis, right? And the null is simple, equal to some number. This is a number. This is an unknown population mean. So what you're saying is the mean income for the young population in Korea is equal to some number. Okay? Like $30 per hour. That's average income. Things like that. The alternative says, no, it's bigger than $30 per hour. An alternative like this is called the one-sided alternative. This is called two-sided. Right? I consider the first one, the one-sided alternative. And in that presentation file, you have two-sided test procedure, okay? So it's a question of a population mean. What we can do is you draw a random sample, small sample, like 200 observations out of population, and you can calculate the sample mean, y bar. And we learned that the mean of the mean is equal to the population mean, right? And then variance of the mean is this, right? We did these calculations the last time. And we can actually go further. If the sample size is big enough, y bar is approximately normal distribution with mean and variance. So how large is large enough? It really depends. But typically, the sample you're going to have is big enough. So we can trust this. So that's the background. There are two methods of testing, right? There's a rejection region method, and there's a p-value method. So the idea is very simple. Now we know that y bar follows this normal distribution. So if you draw a different sample, you can draw a different y bar here and there. Now suppose that the null is true. Can you say more about this distribution? So here, mu is unknown, right? If we assume that the null is true, we can use the value under the null. So y bar follows the key difference is you can fix the center of y bar if you assume that the null is true. So center is fixed. And suppose that the sigma squared is known. If it is not, you can estimate it. You can use the sample variance. So center is fixed. standard deviation is known. So everything about this distribution is known, right? So you can calculate the probability. So the idea is, now distribution of y bar looks like this. If you draw one sample, and suppose that your y bar is like this, very close to mu null, which is true under the null, then there is a kind of good chance that the null is true, right? Now suppose that your y bar is far from the center, mu 0. And there is a better chance that the alternative is true, right? Because that's what the alternative says. So that's the idea. So the rejection region method basically says the rejection region in this problem looks like this, y8. So we like to fix certain value y of a, and then you draw your sample. If your y bar is in the rejection region, then we reject the null hypothesis. Okay, that's one idea. Because your sample mean is far from the population mean under the null, there is a better chance that the null is false. Now, what is unknown is this value. What's the cutoff? How do you determine the rejection region? So for that, we use the type 1 error. So let's recall this definition. Now suppose that we are going to use the rejection region method. When do you reject the null? What's the meaning of rejecting the null hypothesis? When do you do that? Whenever your sample mean is in the rejection region, right? That's the meaning of rejecting the null hypothesis. Now, what's the meaning of the null is true? Now, if the null is true, the center of y bar is going to be this value, like $30 per hour. So we can fix the distribution. Okay, so that's the meaning of these two sentences. So let's use them. Rejecting the null means y bar is in the rejection region. Given that the null is true means y bar has this distribution. Okay, so this conditional probability is equal to the significance level, which is usually given. Now it follows a normal distribution. So to find out the probability, we standardize it, right? We subtract the mean of a random variable, which is mu 0 under the null, and we divide by the standard deviation. When you do it, you have to do it on both sides. So I standardize this inequality, right? I subtract the mean and I divide by the standard deviation. And this is your t value, right? As you standardize it. Or to be exact, this is your g value. because we assume that the population variance is known. I think I use every information in this statement, so let me just drop this conditional statement. So that's equal to alpha. Now suppose that somebody, maybe judges, Congress, whoever, or your teacher, says that alpha can be 0.05, 5%. So you can tolerate this much errors, type 1 errors. Okay, when you do this kind of work, sometimes you're going to make a mistake. The frequency of this particular type of mistake, type 1 error, should be less than 5%. It cannot be more. Okay, suppose that that's given. Then can you find out this y of a? So that's the famous 1.96. Okay? And this value is 1.96. Oh, is it correct? No, it is not. Sorry. 1.64. So from the standard normal distribution, 95% of probability mass is on the left. 5% is on the right. And that point is 1.64. Right? So YA in your rejection region is mu naught plus 1.64 times sigma divided by square root of n. So that's your rejection region. So I just solved it. I multiply this number on both sides and put mu naught on the other side. And that's y of a. Now, everything here is known. How do you know this mu naught? The null hypothesis says mean wages is $30 per hour. 1.64 is a number, so we know. Where is the sigma? You assume that it is known in this problem. If it is unknown, then you can estimate this using the sample information. The only difference is we call such a thing a p-value, not g-value. Right? That's the only difference. Everything else stays the same. So the rejection region is determined. This is just one number, like 32.5, for example, depending on these quantities. And then what? You draw a sample, just one sample. Get the sample mean. If it is bigger than this cutoff, 32.5, what do? You reject the null hypothesis. If it is not bigger than 32.5, you don't reject the null hypothesis. Okay? So that's how you make a decision. In such a rule, the probability that you commit a type 1 error is less than 5%. At least we can guarantee. Okay? So that's the first method. Is everything clear? If it is not, you can read my my presentation file. So that's the first method, the rejection region method. The second method is the p-value method. So what is p-value? p-value is a conditional probability of some kind. So the condition is the null is true. So what kind of probability we like to calculate? So suppose that you draw your sample already and you observe y bar. Okay, let's call it small y bar. So this is the observed sample mean. Now this is a thought experiment. You're asking, what if I draw another sample? What is the chance that from my second sample, the sample mean there is as big as the sample mean of my first sample, or even bigger? Okay. Now this inequality really makes people very uncomfortable. So let me just erase it. I'll put it later, okay? Let me try it again. You already have your sample mean. That's your evidence. That's your data. And you're simply asking, what if I do it again? So suppose that there is a suspect, right? This guy, person, is very suspicious, have some blood in his hands. And you collect your evidence. That's it, investigation. That goes against the suspect, okay? So that's your small y bar. And then you're asking this. What if this happens all by chance? Okay? So what if I repeat everything again, am I going to get the same evidence as strong as the evidence I have right now? Okay, that's the p-value. So that's the meaning of this probability. Assuming that the null is true, assuming that he is innocent, let's assume that. And you're asking, what if? You just repeat the same thing all over again. What's the chance that everything just happened like that? Although he is innocent. Okay? Now there's one problem though. Y bar is a continuous random variable. So for a continuous random variable, the probability of y bar equal to one value is always equal to 0. So it's not just interesting at all. So that's why we put an inequality, just to calculate something. Otherwise, the answer is always 0, right? So that's meaningless. So the textbook explanation is the p-value is the conditional probability that we assume that the null is true, and then we draw another sample just in your mind. We actually don't do that. We don't repeat the investigation. You simply ask, what if, believing that he is innocent, I repeat my investigation and get an evidence as strong as my current evidence or even stronger? Okay, that's the p-value. So how do you actually calculate this? Same as before. So if the null is true, you can fix the distribution. Now everything here is known. This is a sample mean from your sample. This is the value under the null. This is assumed to be known. This is the sample size. So this is all fixed. So you can calculate this probability. Suppose that it is 0.001, much less than 0.05, which is like. Now what? What is the decision? So there are two possibilities. This is a conditional probability, right? So one possibility is your assumption is true. He's innocent. Just all by chance, it happened like that. He appeared to be guilty. Okay? And that probability is very small, by the way, 1 in 1,000. If you believe that he is guilty, an event that is very unlikely to happen just happened to you. And the chance of that event is 0.1%. So something shouldn't happen, just happened to you, if you believe that he is innocent, if you believe the no. So that's option 1. You just keep believing it, okay? Or maybe your assumption is wrong. Okay? So that's why, in this case, we reject the no. Because we don't usually believe that that rare event just happened to you. Perhaps it's time to doubt our assumption, the no. So we reject the null hypothesis. Okay, so that's the p-value method. So that's the idea. Usually, things are a lot easier. R reports this g-value or t-value, whatever that is, and R reports the p-value too. So you can just use the outcomes from the computer, and you make a decision. Okay? I guess you have to know what to do under different circumstances. So that's an introduction. So when you come back, so what's the plan? Tomorrow there's no class. Next week on Tuesday, we're going to solve questions together. So be prepared, okay? To solve the past exam. And then on Wednesday, we'll have an exam. And then next week, we are going to continue our discussions. Okay, I'll see you.